Now that we have an expression for our chemical potential, which we substitute into our equilibrium condition, we can derive this equation of the substitution. Divide by RT and rearrange a little bit to prove that this equation must then be equal to 0. We can now take this group of terms to the other side of the equation with a negative and realize that the sum of stoichiometric numbers multiplied by the Gibbs free energy of each of the components in the standard state gives the standard state change in Gibbs free energy of the reaction, similar to the standard state change in enthalpy or heat of the reaction like you calculated it in SIR. This beautiful pi symbol over here means that I have to take the product over all the components I, not the sum of this fugacity ratio of each of the components raised to their stoichiometric number. And remember, this is negative for reactants and positive for products. This fugacity in the mixture will change as the composition is changing, and there is therefore only one composition set where the parameter on the left-hand side is equal to this group of terms at equilibrium on the right-hand side. This means that we can then use this group of terms to calculate our equilibrium constant. This equilibrium constant is now a function of thermodynamic parameters. It is subsequently not a function of pressure, because this is determined at the standard state pressure, which is 1 atmosphere or 1 bar. It is also not a function of composition. It only needs you to know the stoichiometric coefficients of each of the components in the reacting mixture. It is, however, a function of temperature. This temperature refers to the temperature of your reacting mixture when equilibrium is reached, and you need to determine the standard state Gibbs free energy, which is at 1 atmosphere and 1 bar, but at the reaction temperature. So just to clarify, this temperature should be the same as the temperature referenced in the tables where you got the standard state values from. And for the tables that we are going to use in this course, it means that this temperature must always be 298 Kelvin, because we can find values for our standard state Gibbs free energy at that temperature. However, this temperature must also be the same as that of our reacting mixture when we reached equilibrium. So it may seem as if we are going to be stuck calculating equilibrium compositions only for mixtures at 298 Kelvin. That's not true. We are going to make a plan to convert this equilibrium constant to other temperatures. At equilibrium, this parameter that is a function of the concentration in the mixture, let's call this ln Q, must be equal to this thermodynamically determined parameter, the equilibrium constant, or ln of the equilibrium constant, which is only a function of the stoichiometry of the reaction and the temperature where the reaction is taking place at equilibrium. From the definitions and the ideal gas implications of the fugacities that we discussed previously, we can realize that since the fugacity in the mixture is equal to its partial pressure, and at the standard state it is simply equal to the pressure at the standard state, therefore 1 atmosphere or 1 bar. Remember, the units must be the same. At equilibrium, this group of terms will be equal to our equilibrium constant. Often the subscript pressure here, Kp, is used to indicate that the fugacities is expressed in terms of pressures and partial pressures, and the ideal gas assumption holds. For liquids, this ratio depends on whether we've got ideal mixing or not. In the case of non-ideal mixing, we must calculate it as an activity of each component, which results in this expression. For ideal solutions or ideal mixing, it is simply a function of the mole fractions of the liquids in solution. This statement may be a bit confusing. So if we have a mixture of different phases in the same system, if we, for instance, have a solid that gets oxidized with oxygen in the gas phase to form this oxidized solid component, what you need to realize is that you have two solid phases present there, and that each of the solids has a composition of mole fraction 1 for solid red in the red phase and mole fraction 1 for solid blue in the blue phase. Meaning that if we consider their fugacity ratios in our equilibrium constant expression, it will be equal to mole fraction 1 divided by mole fraction 1 for each of the solids.